Hi everyone, it's Yan again. In this week, we'll learn about probability, normal distribution, and z-scores. What is probability? Probability is the chance of getting certain outcome from a random event. A random event is any event where the outcomes observed in that event can vary. If we roll a dice, we expect to see 1 or 2 or 3 or 4 or 5 or 6. So dice rolling is a random event because the outcome varies each time you roll the dice. The way we compute probability is to divide the frequency of times an outcome occurs by the number of total possible outcomes. It's also called a sample space. For the dice example, say we're interested in the dice giving a number 5. The frequency of the dice giving a number 5 is 1. The sample space, the total possible outcomes, is 6. So the probability of the dice giving a number 5 is 1 divided by 6. Is 0.16. Probability can be written as a fraction, decimal, percent, or proportion, but its value must vary between 0 and 1. The closer to 1, the more probable an event is. The closer to 0, the more improbable an event is. So an event can either be probable or improbable. It can never be a negative value. Now, suppose our experiment is to measure the weight of newborn babies. In this graph, the x-axis is the birth weight, and the y-axis is the frequency count. The study itself is not important. I'm just using this graph as an example. So the birth weight is a continuous random variable. And continuous variables have unlimited number of possible values. If we use the same formula to predict the probability of certain weight, the denominator will be a really large number, and the numerator will be 1. Effectively, the probability will be 0, and that's useless to us. Therefore, we have to use another approach to estimate the probability. The equation we use to calculate the probability of a continuous random variable is called probability density function. When we say a normal distribution is mathematically and theoretically defined, we mean the probability density function defines a normal distribution by relating each score distributed along the x-axis with each frequency distributed along the y-axis. In this graph, the probability density for score 0 is a little bit less than 0.4, and the probability density for score 1 is almost 0.25. I attached a Khan Academy video in our learning module if you are interested in PDF. But all you need to remember is a normal distribution is mathematically and theoretically defined. You don't need to memorize this equation. The second characteristic of a normal distribution is it is theoretically defined. We know a normal distribution is mathematically defined by the PDF equation, but our behavioral or clinical data rarely fall within the limits of this equation. They usually approximate a normal distribution. This histogram is the frequency distribution of birth weights in 3,226 newborn babies. This distribution can be estimated by the superimposed smooth bell-shaped curve because we assume if we could look at the entire population of newborns, the distribution would have been the bell curve. Another characteristic that requires attention is number 7. The total area under the curve of a normal distribution is 1. I'll use the same example of rolling dice, though it is a discrete probability distribution. It is discrete because the number of outcomes is limited, but it is more visual to explain this characteristic. So there are 6 outcomes when you roll a dice: 1 or 2 or 3 or 4 or 5 or 6. So the probability of each outcome is 1 out of 6, or 0.16. We add them all up. We add all these 0.16 up, and we get 1. Now imagine that the discrete variable turns into unlimited continuous variable along the x-axis. And you add up all the probabilities and in the area under the curve. It should be 1. The other characteristics of normal distributions are the mean, median, and mode are all located at the 50th percentile. That means that half of the data in a normal distribution fall above the mean, the median, and the mode, and half fall below. A normal distribution is symmetrical. That means distribution of data above the mean is exactly the same as those below the mean. A normal distribution is defined by 2 parameters, the mean and the standard deviation. The mean can equal any value from the positive infinity to the negative infinity, and the standard deviation can be any positive value. Well, in this graph, the green distribution has a mean of -2, and both the red and the blue have the mean of 0. For the red distribution, the standard deviation is larger than the blue one, so the red distribution is more spread out, and the blue one has a smaller standard deviation, so the distribution is more clustered. But there is a typo in this graph. It says up here it's a standard deviation, which should be represented by sigma, and down here they use the sigma squared, which is a variance. So the last characteristic of a normal distribution is the tails in a distribution are asymptotic. That means tails of the distribution are always approaching x-axis but never touch it. This allows for possibility of outliers in a data set. Does this figure look familiar? It's on page 111, empirical rules. For normal distributions with any mean and any variance, the empirical rule applies, and it states at least 68% of all data lie within 1 standard deviation, and 95% lie within 2 standard deviation, and 99.7% lie within 3 standard deviations. 95% of data fall within 2 standard deviation, and this is defined as the statistical norm. Since all normal distributions follow the empirical rule, it is easier to calculate if we transform normal distributions to one standard distribution with a mean of 0 and the standard deviation of 1. This way, we only need to calculate the areas under the curve for one distribution to estimate the probability. This special normal distribution with a mean of 0 and a standard deviation of 1 is called a standard normal distribution, or Z distribution. Z-score is distributed along the x-axis. Since the mean is 0 and the standard deviation is 1, Z-score is both the distance from the mean and the number of standard deviations from the mean. To compute the Z-score, we divide the deviation by the standard deviation, and for population, standard deviation is represented by sigma. And you see the area under the curve has been divided into 8 sections, and the proportion of each section has been provided as decimals. And the way to use this is to interpret the proportion of the area as the probability. For instance, the probability of locating a score between -1 and the mean 0 is this area, and the probability is 0.3413. And remember, at the beginning when we introduced the probability, we said that probability can be written as a fraction, decimal, percent, or proportion, and here it is written as a decimal. And we also discussed why we cannot calculate the probability of just one single score, because the result will be almost 0. This is an example to show how to transform a normal distribution to a standard normal distribution, or Z distribution. A researcher measures the furthest distance in feet that students move from a podium during a presentation, and the data were normally distributed with a mean of 12 and a standard deviation of 2. So what is the Z-score for score 14? Now you can pause the video and see if you can compute the Z-score for 14. So the Z-score is the deviation of the score from the mean divided by standard deviation. So it's 14 minus 12 divided by 2. So the Z-score is 1. So for a score of 14 in a standard normal distribution, and the location is a Z-score of 1. Unit normal table is also called a Z-table. It's a probability distribution table displaying a list of Z-scores and the corresponding probabilities or proportion of areas associated with each Z-score listed. We already learned that the probability of locating one single score will be close to 0, and you can see it from this table. When the Z-score is 0, which is actually the mean, the probability is 0.0000, which is actually not 0. You can imagine that after quite many zeros, there is a 1 somewhere. But it's such a small number, so even if you keep 4 decimal points, it's still rounded down to 0. Now let's pretend that this orange bar is a sliding door. It can move to the left or the right. And at this point is the Z-score 0.02. The probability of getting a score between 0 and 2 is this orange area. So the probability is 0.0080. Now the probability of getting a score larger than 0.02 is this white tail, the area in this white tail, and it's a 0.4920. is the area beyond the z in tail. And here is the z-score. And if you add 0.0080 and 0.4920, and you have the 0.5, and that's a 50%. It's the half of this area under the curve. If you want to find out the probability of getting a score smaller than 0.02, what do? You add up this white half and this orange area. So it's a 0.5 plus 0.008, and you will get 0.508. That's your probability of getting a score smaller than 0.02. The next few slides are examples from our textbooks. If you don't have problems, you can skip it. Or you can go through the video and work on the problems with me together. This is the example from page 136, a normal distribution with a mean of 5.2 and standard deviation of 1.6. So what's your probability of obtaining a score larger than 6? The mean is 5.6, and one standard deviation away is 6.8. So 6 is between the mean and the one standard deviation. 6 should be over here. To obtain a score smaller than 6, so we should add up this area and the pink area. The z-score is the deviation divided by standard deviation, so the z-score is a 0.5. And then you go to Appendix B on page 478 to locate 0.5 in column A, and then the pink area should be 0.1915, and that's the proportion of this area. So the probability is 0.5 plus 0.1915, and 0.69 is your probability. This is an example on page 137. The normal distribution has a mean of 24 and the standard deviation is 12. And the question is, what's the probability of obtaining a score smaller than 13? And we need to calculate this area, the pink area. And in the unit table, the tail is on the right, but the normal distribution is symmetrical, so the size on the right or on the left should be the same. The z-score is negative 0.92, So in the appendix B on page 478, you need to find 0.92 in column A. And it should be somewhere over here. So the tail in the right is 0.1788, and it's symmetrical, so the tail on this side is the same size as the tail on this side. So that's your probability, 0.1788. This is an example on page 138, a normal distribution with a mean of a 7.5 and standard deviation of a 2.5. So what is the probability of obtaining a score larger than 4.1? And it should be this pink area plus half of the distribution. The z-score for 4.1 is a negative 1.36. And imagine it's on the other side of this distribution over here somewhere. So you go into appendix B on page 479 and look for 1.36 in column A. And the column B should be the size of this area, the pink area. So your probability will be the pink area plus 0.5, and it is a 0.9131. This example is from page 140. The normal distribution has a mean of 20 and the standard deviation is 9. And what is the probability of obtaining a score larger than 11 and smaller than 29? So they're asking the proportion of these two areas together. We'll calculate two z-scores. Z-score for 11 and a z-score for 29. And then it's -1 and a +1. And we know in the unit table we only have this area, the proportion of this area. But we also know the normal distribution is symmetrical, so the other side is the same size. So we go to appendix B, find the z-score 1 in column A, and then the column B is what we need. It's a 0.3413. And then we plus another 0.313. The probability is 0.6826. This is the example from page 140. We have a population mean of 100, standard deviation of 15. So what is the minimum score that you need to get into the top 10%? So top 10%, we know it's in the right tail, this pink area. And first of all, 10% equals 0.1000. And we're looking for the z-score over here. And when we go to appendix B on page 478, we don't see 0.1000, we see two close ones. And one is a 0.1003 and the other one is a 0.0985. And if we can draw the line next to this orange bar, and the 0.1003 should be to the left of this bar, and a 0.0985 should be to the right of this orange bar. And we're looking for minimum score. So if we pick this one, if we pick the second one, we'll leave some scores out. So we're going to use this 0.1003. And the z-score is 1.28. The z-score is here. We plug it in and calculate x. So the minimum score is 119.2.